Welcome back to the next installment of this series. To begin, we'll talk about statistical learning. Statistical learning provides a framework for understanding relationships between independent and dependent variables. Statistical learning is important for developing accurate predictive models in machine learning. In machine learning, the primary aim is to predict unknown outcomes based on known inputs. Machine learning also primarily focuses on pattern recognition and prediction efficiency. The main difference between statistical learning and machine learning is the emphasis on interpretability and theoretical understanding in statistical learning, while machine learning often prioritizes predictive accuracy and computational efficiency. To put it simply, statistical learning ensures that machine learning models are not only effective, but also comprehensible and reliable in their predictions. Statistical learning is about finding a relationship between an independent and dependent variable. This relationship can be denoted using the formula y equals f of x plus epsilon. Dependent variables are denoted using y. Dependent variables are the variables that are measured and often called output variables or the response. Independent variables are denoted using x. Multiple independent variables can be denoted as x1, x2, x3, so on and so forth. Independent variables are the variables you can change and go by different names, such as input variables, predictors, and features. The function f represents the systematic information that x provides about y. The function f may involve many input variables. The function f models the expected value of y based on x. This reflects the complexity of the models used in data analysis. Epsilon is a random error term in statistical models. The error term captures the data's variability not explained by the model. It is independent of x and assumed to have a mean of 0, often following a normal distribution. To make predictions based on this relationship, we use an estimated function f hat that approximates the true function f. This estimation allows us to apply the model to new data, where the predicted response, denoted as y hat, is generated using the estimated function applied to the input variables. Y hat equals f hat of x represents the predicted value of the response variable y. We're going to focus on why we need to estimate f. There are two main reasons for estimating the function f. The first reason for estimating f is for prediction, where the inputs x are known, but the output y is not directly observable. A prediction-focused approach is useful for a surface-level understanding. In prediction, since the error term averages to 0, we predict y using y hat equals f hat of x. In this case, f hat is often treated as a black box, focusing on accuracy rather than the model's form. Prediction deals with questions such as, is this house under or overvalued? These questions focus on accurately estimating outcomes based on the available data. For prediction, nonlinear models are often favored for their ability to capture complex patterns. The second reason for estimating the function of f is for inference. If a deep understanding is the goal, then inference is the appropriate choice. Inference aims to understand the relationship between variables and generalize these findings. Inference involves questions like, how much extra will a house be worth if it has a view of a river? In inference, the goal is to quantify the impact of specific features on outcomes. Linear models are mostly associated with inference due to their straightforward interpretability. In prediction, the accuracy of y hat depends on two types of error. The first error is the reducible error. It comes from the difference between the true function f and our estimation f hat. Reducible error is influenced by model bias and variance. Minimizing reducible error involves refining f hat using appropriate statistical learning techniques and aids in closely approximating f. The second error is irreducible error. No matter how well we estimate f, the irreducible error cannot be eliminated. Irreducible error is associated with inherent data variability. This variability includes measurement errors and unobserved variables. Irreducible error also affects prediction accuracy. Expected value provides an average or mean of a random variable. It represents the central tendency of the data or predictions. Variance measures the variability of a random variable around its expected value. This spread of variance indicates the level of dispersion in the data. Variance also indicates the uncertainty in the model's prediction. In inference, our aim is to estimate f, but the goal is not necessarily to make predictions for y. Instead, we focus on the underlying relationships within the data. We also analyze how different models behave under various conditions. There are three essential questions of interest when dealing with inference. The first question is, which predictors are significantly associated with your response? This involves identifying the most influential predictors. The second asks, what is the nature of the relationship between the response and predictors? This includes determining whether the relationships are positive or negative. The third question asks if the relationships between the response and each predictor can be summarized using a linear equation, or is it more complex? Often, true relationships are more intricate. This means that a linear model may not provide an accurate representation. Now let's discuss how to estimate f. Statistical learning begins assuming an observed set of n distinct data points. These data points are referred to as training data. Training data is used to train or teach a statistical learning method how to estimate the function f. The function f represents the underlying pattern or relationship in the data. The goal is to apply a method to this training data to accurately estimate the unknown function f. Most statistical learning methods fall into two categories. The first category is parametric. Parametric methods involve assuming a specific form for f. An example of a parametric method is a linear regression. This method involves estimating the parameters based on the data. The second category is non-parametric. Non-parametric methods do not make explicit assumptions about the form of f. Instead, non-parametric methods focus on constructing a model that adapts to patterns observed in the data. Non-parametric methods adapt more flexibly to the inherent complexities of the data. Parametric methods involve a two-step model-based approach. The first step is an assumption about the functional form or shape of the model. In other words, selecting the model. The second step is fitting the model to the training data. You can use the least squares method to simplify the estimation of f. A disadvantage of the model chosen is that it might not accurately reflect true f. This may lead to model misfit. To address this, more flexible models may have to be considered. Flexible models allow for greater adaptability to the data's inherent complexities. Caution is needed to avoid overfitting. Overfitting occurs when a model follows the training data errors too closely. This impairs the model's performance on new data. Non-parametric methods do not make assumptions about the form of the function f. This avoids risks associated with incorrect model specification inherent in parametric methods. Non-parametric methods do not simplify the problem by reducing it to a few parameters. This means non-parametric methods generally require more data. This is especially true as the complexity of the data increases. An example of a non-parametric method is the thin plate spline. Thin plate spline is particularly useful for smoothing and interpolation in multi-dimensional data. Thin plate spline offers flexibility in capturing complex patterns. It does this without assuming a specific form of f. In order to fit a thin plate spline, the data analyst must select a level of smoothness. Choosing the correct level of smoothness is crucial. The more smoothness, the less responsive the model becomes to fluctuations. These fluctuations come from the training data and can cause the model to deviate from the true function f. This excessive variability is an example of overfitting. Overfitting is when the model captures noise instead of the underlying signal. This leads to poor performance on new data. In general, as the flexibility of a method increases, its interpretability decreases. Restrictive models have greater interpretability. If inference is the primary interest, then restrictive models are favored. Linear regression and lasso are two linear models that are used for inference. This is because the relationships between the response and the predictors is easy to see. Linear regression using least squares, while relatively inflexible, is quite interpretable. Lasso is another form of linear regression that is slightly less interpretable than plain linear regression. Generalized additive models are nonlinear models that are used for inference. Generalized additive models offer more flexibility than linear regression. They do this by allowing nonlinear relationships between predictors and the response. Highly flexible, nonlinear methods like bagging, boosting, support vector machines, nonlinear kernels, and neural networks provide powerful predictive capabilities. This is often at the cost of interpretability. Most statistical learning problems are either supervised or unsupervised. Supervised learning involves fitting a model that relates predictors to a response. It aims for accurate prediction or inference. In other words, understanding relationships between predictors and a response variable. There are classical and modern methods used in supervised learning. Linear regression and logistic regression are what are known as classical methods. More modern approaches include generalized additive models, boosting, and support vector machines. In unsupervised learning, we only have predictor measurements without a response variable. This makes it impossible to fit models like linear regression. Unsupervised learning aims for inference. In other words, understanding relationships between observations without a response variable. Clustering is a common unsupervised learning method. Clustering identifies groups within data based on the predictors alone. It's useful in situations like market segmentation, where the response information is unavailable. Clustering problems can be straightforward when groups are well separated, but challenging when there is an overlap. Visual inspection of scatter plots can help identify clusters when dealing with few variables. With more variables, automated clustering methods are necessary. Statistical learning methods are selected based on the response type. Responses can be characterized as either quantitative or qualitative. Quantitative is numerical. Variables include a person's age, height, income, the value of a house, or the price of a stock. Methods applied to quantitative responses tend to be regression. For example, least squares linear regression uses a quantitative response. Qualitative is categorical. Variables include a person's marital status, married or not married, brand of product purchased, brand A, B, or C, whether a person defaults on a debt or cancer diagnosis. Methods applied to qualitative responses tend to be classification. Logistic regression is typically used with a qualitative, two-class, or binary response. Some statistical methods can be used for either quantitative or qualitative responses. Examples include k-nearest neighbors and boosting. In statistics, there is no universal solution. No single method outperforms all others across every possible dataset. It's important to know a variety of statistical learning methods. This is because no single method is best for all datasets. To effectively evaluate the performance of a statistical learning method, it is essential to assess its fit against a given dataset. A reliable indicator is the mean squared error, which is commonly used in regression analysis. A small MSE indicates that the predicted response closely matches the actual responses, whereas a large MSE suggests discrepancies between predictors and actual outcomes. The primary objective is to verify the accuracy of predictions on unseen test data, ensuring the model's applicability in real-world scenarios. The goal in assessing test MSE is to identify the method that achieves the lowest training MSE. However, a low training MSE does not necessarily guarantee a low test MSE. This underscores the complexity of finding a model that generalizes well beyond the training data. Smoothing splines aid in model fitting by minimizing a residual sum of squares criterion, subject to a penalty for smoothness. This approach helps in adjusting the model to the data's inherent patterns without overfitting. The flexibility of a model as measured by its degrees of freedom influences the training MSE. Generally, increased flexibility leads to lower training MSE, but it may also result in higher test MSE if the model overfits the training data. Overfitting occurs when a model identifies patterns in the training data that do not exist in the test data, leading to poor predictive performance. Cross-validation is a crucial technique used to estimate the test MSE, particularly when the test data are not readily available. By leveraging parts of the training data to simulate test scenarios, cross-validation helps in assessing how well a model is likely to perform in practice, thus aiding in the minimization of training MSE. The expected test mean squared error for a given value, x sub 0, can be decomposed into the sum of three fundamental quantities. The first quantity is the variance of f hat, x sub 0. The second quantity is the squared bias of f hat. And finally, the variance of the error terms. To minimize the expected test MSE, we need to select a statistical learning method. This learning method should simultaneously achieve low variance and low bias. Variance is the amount by which f hat changes if it is estimated using a different training dataset. This balance directly impacts the effectiveness and reliability of the model's predictions. Bias refers to the error that is introduced by approximating a real-life problem. This problem may be extremely complicated, yet analyzed by a simple model. As a general rule, as we use more flexible methods, the variance will increase and the bias will decrease. The relationship between bias, variance, and test MSE is referred to as the bias-variance trade-off. Error rate is the proportion of mistakes a model makes when applied to training data. A check variable is set to 1 if the predicted and actual outcomes don't match, and 0 if they do match. If the check variable is 1, then the specific data point was incorrectly classified by the classification method. This forms the basis for training error rate. The training error rate is calculated using the data that was used to train the classifier. Similarly, the test error rate uses a different set of data points and is calculated in the same way. A good classifier aims to minimize the test error rate. In this context, a conditional probability is the likelihood that the outcome equals a specific value, given the observed predictor. The Bayes classifier is known for having the lowest possible error rate based on the probabilities computed from the data. It includes a decision point called the Bayes decision boundary, which is where the classifier switches from predicting one class to another based on a 50% probability. The Bayes classifier is known for having the lowest possible error rate based on the probabilities computed from the data. It includes a decision point called the Bayes decision boundary, which is where the classifier switches from predicting one class to another based on a 50% probability. The Bayes classifier serves as the ideal standard to compare other methods because it achieves the lowest possible test error rate, known as the Bayes error rate. This is considered the irreducible error, which means it's the best performance any classifier can achieve given the data. One example of a method that uses this approach is the k-nearest neighbors classifier. The KNN classifier identifies the k closest data points to a new observation and estimates the likelihood of each class based on how many of these points belong to each class. As k increases, the classifier becomes less flexible and decision boundary more linear. Choosing the right level of flexibility is crucial for any model success in both regression and classification settings. Achieving this balance is complex due to the bias-variance trade-off, which usually results in a U-shaped curve for the test error, making it challenging to optimize model performance. Statistical learning involves understanding and modeling the relationships between independent and dependent variables using mathematical formulations. Estimating the function f is essential for predicting unknown outcomes from known inputs and understanding the relationships between variables for deeper insights. Prediction and machine learning involves using models to forecast unknown outcomes based on known data, focusing primarily on accuracy and efficiency. Inference seeks to understand and quantify the relationships and effects between variables, often using models to draw conclusions about the data's underlying structures. Estimating f involves selecting a statistical model that best captures the relationship between inputs and outputs from the available data. Parametric methods assume a specific form for the function f using a predefined equation to model the relationship between variables. Non-parametric methods make no assumptions about the form of f, adapting more flexibly to the data's inherent complexities. Increasing a model's flexibility often reduces its interpretability, necessitating a balance to achieve both accurate predictions and understandable results. Supervised learning uses labeled data to predict outcomes, while unsupervised learning finds patterns and structures in the data without predefined labels. Regression predicts continuous outcomes, whereas classification categorizes data into predefined groups, addressing different types of predictive modeling challenges. Evaluating a model's performance involves comparing its predictions against actual outcomes to determine its effectiveness. The quality of fit for a model is typically assessed using statistical measures like mean squared error, which indicate how well the model's predictions match the actual data. Bias-variance trade-off involves managing the trade-offs between bias, which is the error from erroneous assumptions in the model, and variance, which is the error from sensitivity to small fluctuations in the training set, to optimize model accuracy. In classification, the goal is to predict discrete labels for data points, assessing models based on their error rates and accurately categorizing data. Thank you for joining me today as I attempt to unravel artificial intelligence and machine learning. My name is Angel Sanchez, and I'm currently teaching myself to become an expert in artificial intelligence by developing a free online course to document my learning. This journey is not just about acquiring knowledge, but also about sharing and growth. I'm learning as I go, and I invite you to be a part of this learning process with me. If you have found this content insightful, or if you have suggestions or corrections, please comment below or give feedback. Also, check out the resource below in the description that I use when creating this video. More specifically, my use of the book, An Introduction to Statistical Learning with Applications in Python, of which this course will be based on. Your input is invaluable as it helps me and others learn more effectively. Don't forget to stay tuned for the next part of this series, where we'll dive even deeper into the mechanics and applications of machine learning. Remember to like, share, and subscribe if you're excited to join me on this journey. See you in the next video.